Bill Greene, Senior Director of CPU Engineering at ARM. Here we go. Thank you.
Hey. Thanks, Claudia. Well, we're on the home stretch, folks. Just one more keynote and a panel between us and the bar. So thanks for hanging in there. Thanks for the introduction, Claudia. My name is Bill Greene. I'm based up in Austin, just up the road, and I lead the ARM CPU engineering team, where we're developing the highest performance CPUs that ARM makes. And these processors go into mobile devices like smartphones and laptops, as well as servers in the data center, and even autonomous vehicles. So they go into high performance applications. But I'm here today to talk about the other end of the spectrum. I'm going to talk about our tiniest, most power efficient processors. And this talk will be focused on how new compute capability is really transforming what can be done at the edge of the network. Next slide, please. So ARM is fairly ubiquitous in a wide range of electronic devices, but some of you might not be familiar with what we do. So we develop semiconductor IP, or intellectual property, which is the designs for microprocessors that are integrated into silicon chips by our partners. So our strength is providing a wide range of power-efficient processors with a strong ecosystem of tools and support so everyone can make their products a success. So again, we don't make the silicon, we license the processor designs to hundreds of companies that incorporate them into their chips, which then make it into end products. Next slide. We've been around about 30 years with rather humble beginnings designing the processor for the BBC Micro personal computer, which was a UK thing. And then the Apple Newton PDA, which if you remember from the mid-90s was well ahead of its time. Things really took off when our CPUs were picked up in the first Nokia cell phones, and then Apple used our design in the first iPhones, and now our processors are in nearly every smartphone out there. And also in like every kind of embedded device that you can imagine. The world's fastest supercomputer for the past 3 years in Japan has been running on ARM, and with 158,000 processors, you could expect it would be fast. But as Robert from AMD mentioned earlier today, it looks like they're going to leapfrog past that soon. But as an American, I'm proud for us to have the fastest supercomputer here very soon. The main reason for ARM's success, I think, is our low-power designs and our partnership business model, which enables innovation in any market that uses silicon chips. Next slide. So everybody probably has an idea here, especially of the Internet of Things. It's all those widely distributed devices that are powering a lot of the things that we've been talking about at this conference. In this talk, I'll be focusing on these IoT endpoint devices, which live at the boundary between digital and analog. This is the electronics that's right there between the sensor and the actuators and the networks that connect them. So this diagram kind of puts things in perspective. On the right, we have the cloud data centers, and connecting them to the IoT devices is the edge, which is somewhat nebulous, but you can think of as all the cellular and local networking and some distributed computing between them. In this talk, I'm going to describe how some breakthroughs in hardware and software capability are really driving a step change in the capabilities of these endpoint platforms, allowing them to build vision, voice, and vibration capability coupled with genuine intelligence at the endpoint. Next slide. Oh, sorry, one more. So long ago, Erasmus said, well, he said this in Latin, "In the land of the blind, the one-eyed man is king." And what he meant was that when no one can see at all, even being able to see just a little bit gives you immense capability, immense power. Next slide. And we have a great demonstration of this in something from evolutionary biology called the Cambrian Explosion. 500 million years ago, life on Earth changed quite rapidly. And the reason it did was because creatures called trilobites developed the ability to see. And very suddenly, well, in geologic timescale suddenly, they became very successful predators, and this drove immense pressure on other life forms to adapt. They had to protect themselves by developing armor, moving more fast and quickly, in defense against this new predator, which suddenly became more effective. And 5 years ago, when Masayoshi Son from SoftBank first took control of ARM, He gave a presentation saying that the Cambrian explosion and the IoT explosion, it's the same thing. And what we're seeing now in IoT is the evolution of the ability of these devices to sense their environment, to then make deductions and take actions based on what they see, feel, and hear. Next slide. So it's quite clear that wherever you go, smart sensors, smart devices, smart endpoints are undeniably the future. I think we can probably all agree to that. Let's look at just a few of the basic characteristics of a smart device. On the left, we see an old steam pressure gauge from about 100 years ago. On the right, a modern temperature and humidity sensor from a home. And you can see so many stark differences between the two. On the left, it's dumb, it's analog, it only does one thing. It's fixed in position, you have to actually go to it to maintain it, etc. The sensor on the right has so many corollary advantages. It's smart, it can be reprogrammed and updated, upgraded, it can be managed remotely, it's secure, it's wireless, etc. I think we can all appreciate that this kind of digital smart platform is really the way that sensors are going. Next slide. And so we're increasingly seeing the need to embed intelligence into even the smallest and most constrained devices. You know, it's relatively easy to implement some kind of intelligence in the cloud. You have huge processing power, essentially infinite memory, no problems, or at least different problems with power consumption. But we really can't afford to send everything to the cloud for processing. However, doing this processing on small, cost-sensitive, energy-constrained devices is much, much harder. But it's what we have to do. Unless we do this, the IoT really can't scale, and the rewards of cracking this problem are huge. We talk of sensing and interacting with the environment, which you can think of as some sort of intelligence, in three primary ways: through voice, vision, and vibration, to see, to hear, to feel. There are many other ways, of course, but these are the most common, and many others boil down to the same processing chain as we see here. First, there's signal conditioning, then there's feature extraction from that signal, and then some kind of decision-making algorithm to potentially take action. And generally, the first two are a signal processing problem and lend themselves well to DSP or digital signal processing techniques. The third is much more of a machine learning problem and is often best addressed by some kind of neural network solution. Next slide. And we can build all of this, or start to build all of this, into the tiniest of devices. And we're going to take a look at each of these three realms in turn. Next slide. So let's have a quick look at the application of audio processing to a device. What can you gain from this? Well, a dumb device simply records, stores, and plays back the information, the audio. It's just a tape recorder. It's dumb. It's not capable of analyzing the sound, of adding any value to it. But if you make that device into a smart device, then suddenly you have all sorts of capabilities, almost limited by your imagination. As well as detecting the sound and recording it, you can analyze it, you can act on it. You could then control other devices and connect to cloud services. You could enhance the capability way beyond what this device could do just by itself. Next slide. So there are some advances that we've seen very recently, maybe in the last year or so, that make increasing levels of capability possible on very tiny devices. We have DSP techniques. These can filter out background noise, detect a particular sound even though it's in a noisy environment, use multiple sensors to use beamforming techniques to find out where the sound is coming from or focus in on a particular location. These techniques can even identify particular types of sound, identifying or pulling out speaking voice from some other background noise, and they can transform that signal into a series of discrete features that can then be acted upon. And we can implement more and more of this into a standard microcontroller without the need for a separate DSP accelerator. Machine learning techniques take this processed, filtered, cleaned up signal, and then they do things like extracting individual words from that input stream. They can identify the speaker. They can classify the sound. Is it a siren, a gunshot, an explosion, or some animal noise? And they can transform sequences of words into meaningful questions or commands. So these techniques are well understood, but until quite recently, the assumption was that you had to have a massive GPU or a huge ML accelerator or something that plugs into the data center, because you need huge amounts of computing power, right? Well, this is rapidly becoming not true. In fact, it's not true today. We can do a huge amount of this on a microcontroller platform within the device itself. Next slide. So if we try to break down that chain for audio processing, we have first on the left, something that's on all the time. It just consumes the tiniest little drips of power. It's just listening for something. Is there some voice around here? And we can use a very small microcontroller to do that. As soon as it detects some voice, it fires up the next part of the signal chain, which is looking for the magic word. Alexa, Siri, Google. Hopefully your phones don't all come to life. We can then do more to extract meaningful words, do some natural language processing, and then connect to the cloud or other computers. And so we have this spectrum of compute capability from something that's on all the time, just listening for some sound, then something that can detect the wake word, then something that can detect natural language, and then something that can take action. Next slide, please. So to enable this, we've done a lot of work to optimize CPU performance for these types of applications. On this slide, I'm not going to go through all the details, but this is showing some benchmarks on the keyword spotting algorithm or function. You can note the huge increase in performance of the green bar there. That's the Cortex M55. I think it's still showing the internal code name there. But this is uplift in performance on the keyword spotting function algorithm, but we see similar uplifts for other applications as well. Next slide. And likewise, for typical machine learning applications, for inference and audio processing, we see a 6 to 7x performance gain in the latest generation of microcontroller itself. But the magic really happens when you couple this with a neural processing unit, or an NPU, which is designed specifically to execute ML algorithms really well. Then we see a combined performance increase of 50 times or 25 times the power efficiency on speech recognition. I'll share a little bit more detail about these specific processors a little bit later in the presentation. Next slide. So in the second realm, let's go beyond voice, which people often associate with machine learning, and talk about vibration. This is an increasingly interesting area. And by vibration, I mean signals that change more slowly. This could be temperature, current, magnetic flux, position, orientation. And on the face of it, vibration is very similar to sound, but what we're looking for is often quite different. It might be useful to determine what is normal vibration or normal vibration-like signal, and then extract the abnormal if it's in there. So these are things that you might observe about machinery that when it's operating normally or it's misbehaving in some way. Maybe a bearing is wearing out, maybe the motor is starting to fail, etc. So first, we learn what normal looks like. What does that data look like? And then we average away the normal operation and detect the abnormal part of the signal. Very often this is hidden, but we can use DSP techniques to extract what looks like the abnormal signal. Then we can use machine learning to analyze that, maybe take some action, shut the machine down, change its operating conditions, alert a support engineer or whatever, possibly avert some expensive factory failure. Next slide. And there are products like this in the market right now. What I'm showing here is the Bob Assistant. It's made by ST Micro. The software is by Cartesium. The middleware is the Mbed OS from ARM. And this runs on a Cortex M4 processor at 48 megahertz. Not a huge amount of processing power, but it's capable when attached to a machine to learn what is normal. Then it goes into monitoring mode and detects abnormal behavior and then reports back to a host. So the wonderful thing about this is you don't need to train the device in the cloud or train a model off of the device. You simply attach it to the motor and let it learn. and you don't need any intervention of the cloud. Pretty phenomenal, really. Next slide. So turning now to kind of the third application of vision, this is a very common use case, right? An increased capability here delivers more value from what you can do at the endpoint if you can do visual processing. Clearly there's different degrees of analysis, and these need different amounts of processing power. Object detection is by far the easiest. Is there something here? Object classification is determining what kind of things are in the visual stream. And object recognition, of course, is this person Fred? Is that cat my cat? Etc. Next slide. So there are an increasing number of solutions that can process data on the camera itself rather than having to upload to the cloud. It's simply not scalable with a large number of cameras all feeding gigabytes of data. We can't ship all of that off to the cloud, and some analysis needs to be done on the camera. And this is enabled by providing richer DSP processing earlier in the processing chain, which then reduces the complexity of the final stage of neural network. And the fundamental algorithms of lens correction, color correction, convolution, transformation, all can be done on the camera themselves on a standard compute platform, and we can run ML networks on top of that as well. Next slide. So we've done a lot of work over the past year to prove out what can actually be done in practice on a very simple platform. What I'm showing here is the OpenMV Camera. It runs on a processor, a chip made by ST Micro. It has a simple Cortex M7 processor. You can pick this up for $65 and go tinker with it. And what we've done is on the left, we've shown that you can do object detection. In this case, we can count and classify drink cans in a fridge. Very useful, right? This is all done on the microcontroller. It basically determines the occupancy, what type of cans, and this is all done on that chip, which is part of the OpenMV Camera. In the middle, we have a proof of concept to do stereo vision, and this is by just adding another camera. Here we can do depth mapping, motion measurement, distance measurement, etc. And on the right, we developed an application using this OpenMV Camera to detect faults in face masks on a production line. So as the masks are scrolling by, this camera's looking at them and sending a signal when it sees a mask that has some visual defect. And again, all these prototypes run directly on the microcontroller, which is part of that camera board. Next slide. We've also used the CFAR10 image database to run some benchmarks. And we've discovered that the latest compute solutions that we have increase performance by about 7x for image recognition using this standard data set. So very similar performance uplift as what we saw for keyword spotting for audio processing. Next slide. Another area of significant growth is sensor fusion. Here we combine the inputs from many sensors to increase the value of the data and analytics that we can do. This could be two sensors at the same time, or maybe different types of sensors working together. And a single sensor suffers from several drawbacks, right? It's limited in precision, it's a single point of failure, it has limited spatial and temporal coverage if there's some downtime required, and sometimes it's uncertain without some other sensor or camera to corroborate. Next slide. And by adding a second sensor, or maybe even more, we can increase the capability. We can increase the robustness or reduce the consequences of failure. We can reduce interference. We can expand spatial and temporal coverage. We can increase the accuracy by cross-correlating these multiple inputs, and reduce uncertainty by combining different types of measurement to build a better picture. And as you can see, there's many more benefits besides just reliability. Next slide. And then rather than adding separate processing for each sensor and managing each separately, we can combine multiple sensors into a single fused sensor hub. And these sensors might be measuring vibration, temperature, movement, sound, current, etc. And all these can be fused together into a single processing chain of DSP and ML algorithms, giving you a holistic picture of what's going on. And we're aware of several industrial manufacturers that are doing just this. They're looking to build this capability into the products that they produce for their customers. Next slide. So now let's just spend a few minutes looking at where ARM technology fits into this and how it's fundamentally transforming what we can do at the endpoint. Next slide. So current ARM compute solutions cover the spectrum of power, performance, and price points, from the most constrained to the most powerful. And we've already touched on some of the DSP and ML capabilities. If you also factor in security, which is built into the ARM architecture, safety certification, which is very useful for things like autonomous vehicles, we have a pretty complete offering. Next slide. So historically, the Cortex-M microcontroller product line starts from the very tiny and super low power M0 processor and goes up to the Cortex-M7. All of those CPUs with a little star are suitable to run DSP and ML algorithms. So there's a huge range of performance here between the M0 and the M7. And since introduced about 15 years ago, 70 billion chips with the Cortex-M microcontrollers have been shipped. It's a very, very popular platform. Next slide. But now look what you can do. Recent products have really raised the bar for on-device processing. The new Cortex-M55, which was introduced about a year ago, and we should see products coming out in the next 6 to 12 months, it adds DSP capability directly to the microcontroller. It's called the Helium instruction set. It's basically adding new instructions to accelerate DSP operations in hardware. There's no need to have a separate DSP chip to accelerate this stuff anymore. It's all built into the microcontroller. The benefits are you still have real-time capability, a pretty simple microcontroller interrupt model, simple memory interfaces, etc. And with this, it can handle pretty serious DSP workloads. Compared to the M7, we see 5x performance increase on signal processing and 15x improvement on ML matrix multiply operations, which are kind of the heart of ML neural networks. Advance, please. Next slide. So the simultaneous release of the brand new Ethos U55 NPU, this is a neural processing unit, really changes the game. This is the first NPU accelerator that's designed to work specifically alongside a microcontroller. So it's almost like a micro NPU with a very constrained power envelope. It's a companion device which is meant to work right alongside the M55 processor to accelerate ML algorithms. And it works in conjunction, so the tool chain actually manages the software between the two devices. So you don't have to fiddle with a separate programming model for the accelerator. This NPU provides a 32-time performance in ML performance. And so combined together, this is the reason for the 50 times of performance increase that we saw earlier on real-life speech recognition. Next slide. I'll make a passing mention for the ARM custom instructions, which were announced a couple years ago. This is the first opportunity for the end user, in this case, our customer, which is the silicon developer, right? So they take our designs, they add their own stuff and put it into a chip. They can now add custom instructions by developing their own RTL hardware, which tightly couples into the processor pipeline. So if they have a specific application that they want to optimize it for, you can do that and leverage the microcontroller and extend it with your own defined instructions, whatever they may be. This is fully supported by ARM's development tools. Next slide. So we spend a lot of time on the developer experience to make sure it's the best that you can find anywhere. There's an enormous number of microcontroller development boards out there from almost any silicon provider. It's enabled by real-time operating systems, tool chains, libraries for ML and DSP, and the APIs to connect to any cloud provider. So we're really trying to provide the best developer experience that's possible. Next slide. But if you're looking to deploy or get an ML or intelligent endpoint solution out there, one of the best things is the sheer number of leading edge partners and companies who have supporting technology to help you. There's a huge ecosystem already in place and growing fast. These partners have DSP libraries, ML frameworks and networks, basically ready-made technologies all out there, ready to run on ARM microcontrollers and help you develop groundbreaking products. A lot of companies here are doing some really neat stuff. Next slide. So I'll just wrap it up with a few resources if you want to pursue this further. This presentation was developed by Chris Shore, so he's the point person for endpoint AI at ARM. He's based in Cambridge, UK. This presentation was first given at Embedded World this spring, which is a great conference for this type of stuff. A ton of innovation in IoT being talked about there. And here in the audience, in the front row, we have my friend and colleague, Kobus, who can be a resource for you. He's based here in Austin, or up the road in Austin. There's tons of documentation on our website. All these examples, the prototypes for the OpenMV Camera, they're all there in GitHub if you want to go pay $65 and go tinker. And so with that, I hope you're excited about the possibilities for intelligence at the endpoint. I think we have a real inflection point here, which is about to bring some great things into our lives. Thank you.